Hello folks, welcome to CS-412 Software Security. This is the speedrun of OX02 Secure Lifecycle. The learning goals for today are as follows. First, we want to understand and differentiate software security from software engineering and also know the secure development lifecycle and its phases. So let's dive right in. Software engineering is defined as being concerned with developing and maintaining software systems that behave reliably and efficiently, are affordable to develop and maintain, and satisfy all the requirements the customers have defined for them. It is important because of the impact of large, expensive software systems and the role of software in safety-critical applications. It integrates significant mathematics, computer science, and practices whose origins are in engineering. So this is according to the ACM, and it already highlights some of the key aspects of software engineering, as in developing and maintaining software systems. And it is concerned around the design, the structure, development, best practices, and whatnot. Security is not even mentioned on this core definition, and we will discuss how security actually interacts with software engineering. So software engineering is not a one-shot effort, but continuously evolves. It is rare that you would write an application or a program or a library in one go and then it never changes from then on. Software development, production, maintenance are cost and labor intensive. So it requires a lot of resources to continuously maintain your code, update it to new best practices, add new features, retire old features, and so on. And it's also important to note that software lifetime can outlive hardware. So for example, whenever you're booking a flight, you will be relying on a system that's 40, 50 years old and no longer runs on the same hardware that it was designed to be run on, right? But it's still, these old pieces of code are still around, are being used, and are continuously being updated and changed. Now, this is not a software engineering class. We will not focus on waterfall, incremental, extreme, spiral, agile, or continuous integration, continuous delivery mechanisms. Right, so this is not a class to discuss best software engineering practices. We will follow using the examples based on a traditional software engineering approach, and you can generalize to any other software engineering approach that you would like to use after the class is over, right, or in the company that you will be working on. We will focus purely on the security aspects and where software engineering interacts with security. And for that, we will primarily focus on the secure development lifecycle, which is broken into a couple of phases. And here we just have a circle where one phase follows the next one, and it keeps going one after the other. First, there's requirement analysis, followed by design, implementation, testing, evolution, and then you repeat. Right, so these simple phases all follow each other in this example here. We just use this to highlight some of the security aspects that are necessary at each of these individual steps. You can then apply this to all the other different software engineering approaches that are out there. So let's start with the requirement analysis. And during this phase of your project, you need to define the scope and possible security and privacy boundaries. It's good to enumerate all the kind of data that you want to store, process, and whatnot, and then define a security specification. For that, you would highlight different kind of assets, environments that you would be running, and also an additional list of threat models and possible abuse cases. Right, so during threat modeling, you will list all kinds of threats, the risks that you are taking or your software will be taking, different kind of attack vectors, as in defining how it could be attacked, and the emergency plan, as in how you would react when things go wrong and how you would anticipate certain bad things from happening, and then specifying individual follow-up actions so that if emergency should strike, if something bad should happen, you at least know how to react and you've got a process in place. Security requirements, during that you define a privacy policy, a data management plan, and so on, that is written down, specified as a document, and potentially even released to the customers. You'll also have to analyze any kind of third-party dependencies. What kind of libraries you will be using, what kind of other code you will rely on, and also define how you trust these, how much you trust these third parties, what their update policies are, and different kind of risks for the different dependencies that you will be taking in. In the next step, you'll be looking at the design of your software. And the classic design phase, according to software engineering, focuses on functionality requirements, as in specifying what your software needs to be able to do. And for security, we are actually adding different kinds of security concerns as an integral part of the analysis. During the design, you have to continuously update the threat model as the different kind of requirements change, software is being adopted, as aspects and so on change. For the security design review, during major milestones, we'll have to review the security design and its interaction with the functionality and requirements to see if it is still up to date and actually still correct. And if necessary, we have to go back and update it. We also have to update the documentation. Like the design document is an up-to-date document of requirements and functionality with the different security assessment, referencing the data policies, the threat model, the attacker models, and so on. Next step is the implementation. During the implementation, the design may be slightly refined, but not as much, and the security documents must be updated accordingly. As in, you'll continuously reference back to the security document, figure out what has changed, update it, carry out reviews and analysis, and so on. While you're programming, you should be doing code reviews to ensure that the software is built according to specification and checked for bugs. So that you don't do just functionality testing, but also security testing. And during that, you will have a static analysis to ensure high quality code, which will highlight flaws, vulnerability scanning of external dependencies for exploits. If there's any unpatched vulnerabilities in these libraries left, you'll be writing unit tests, which can then later serve as a basis for testing to ensure functionality and security across components. You'll focus on accountability, for example, using a source code or version control system, which is a rather new change. So a lot of companies in practice may still avoid using revision control systems, right? So you've used this here at several classes, and you've likely seen this being used in practice, but it's not used in all the companies yet. Coding standards, as in adding assertions, documentation, and so on, and continuously run integration tests. So whenever you commit, run your unit tests, run the static analysis, use a linter to analyze the code whenever it is being checked in, right? If the implementation works sufficiently well, there's also the testing phase, right? Any completed component must be rigorously tested before they are fully integrated into the prototype and accepted. And for that, we'll base this on fuzzing, dynamic analysis, and also third-party penetration testing to round off the overarching testing. Fuzzing is a form of probabilistic test generation that will leverage the test cases and unit tests you've already written to then search and find for bugs, right? So this goes way beyond functionality testing and highlights different kinds of vulnerabilities and potential issues in your code. The dynamic analysis will complement fuzzing with heavyweight tests based on symbolic execution and different kind of models and specifications that you will have. And last but not least, as I mentioned, the third-party penetration testing is like some form of external validation after you've done all the initial steps to make sure that, hey, like a new pair of eyes will not find any new kind of issues in the code. The next step will be release, right? Before you release the final prototype and send it to the customers and users, you verify the base assumptions from the initial requirement analysis and design. So this is like a look back over your shoulder. You will do a security review, check for compliance of all the security properties that you have specified, a privacy review, check for privacy policy compliance to make sure that all of this is correct as well, and then review all kind of licensing agreements, for example, for open source software that you will be using, and then reference back to that depending on whatever needs to be changed. After you have released the source code or the prototype and the code of your program to the users, you'll enter the maintenance phase. After shipping the software, you continuously maintain security properties. So you have to track any kind of third-party software that you're using and update it accordingly. So whenever there's a bug being reported in one of the libraries that you have integrated, you may need to update and send out a new version to your users. You need to provide vulnerability disclosure contacts through, for example, a bug bounty program or some public contact through a security.txt file that allows security researchers to get in contact with you whenever they find something interesting. Similarly, there's going to be regression testing. Whenever an update is deployed, you have to recheck the security and functionality requirements. And then you obviously need to figure out a way to deploy updates securely, right? So these are all the different phases of the security development lifecycle. Let's now quickly look at an example, and we'll look at Ubuntu, the Linux distribution for that. And over the years, they've gone through a lot of different phases, slowly rolling out additional software security features, integrating them into the base system, and making the overarching system more and more secure. The kernel has been hardened, user space has been hardened, release after release. And in addition, each release, after it is being publicly made available, receives a lot of updates during a well-defined time span. There are all well-defined policies that are openly accessible that allow you to check when, how long different updates are being sent out, what the dependencies are, and what the base configuration is, allowing you to kind of assess the security features of each Ubuntu version as you are working with it. The configuration follows a safe default approach. Subsystems in this distribution enable flexibility. There's a mandatory access control for compartmentalization that is being rolled out with tight policies. File system encryption as a recent default that ensures that data is secure at rest whenever the system is off, kind of mitigating potential attacks against somebody who would steal your system without having user access to it. Leveraging trusted platform modules, user space hardening and kernel hardening, and so on. And it's interesting to see also how this evolved over the different generations of Ubuntu step by step, and is slowly being integrated and slowly made stronger one after the other. So as a summary, right, we've looked at the secure development lifecycle. Secure software development enforces security principles during development, and software should be seen as a living thing that evolves and changes over time. You'll have to carry out requirement analysis where you look at the threat model, security requirements, you identify third-party dependencies and so on. Then during design, you update and refine the threat model. You'll carry out the security design review to tie back to the initial requirements. During implementation, you look at code reviews, static analysis, you do consistent scans for vulnerabilities, and you write unit tests that can then be used later. During testing, you apply fuzzing, dynamic analysis, but also third-party pen testing. When you release code to customers, you do continuous security reviews, privacy reviews before the programs are being sent out, and also licensing reviews. During maintenance, then you keep checking and tracking your dependencies, and you provide a way to disclose vulnerabilities and add security reports to you. In practice, sadly, security constraints are often considered a burden, and many companies only do lightweight security checking as a form of compliance when the software is being released, or only when bugs are being discovered in the wild. Don't be like that. Actually apply the security principles while you're developing software, and this will make the software overall more secure, better, and lower the maintenance cost of the software as you keep working with it continuously.